next speaker this morning. She traveled the world for her science and her career. She originally is from Bulgaria, moved to New Zealand to do her PhD in applied mathematics in Auckland. She works at NIH in the US. She was at École Normale Supérieure in Paris for some time. Got her first professor position in the UK, in Bristol, and then moved a little bit south of Bristol to Exeter, where she is now holding a professorship in mathematics and healthcare. That's a very interesting dialogue here between the math and the healthcare. She's on several boards. You can see on the program her full villa. She's a high-profile scientist. I had the privilege to work with her for several years on this notion that she is going to walk her through today, this idea that we have a personalized blueprint, a motion signatures that characterize each of us. She's incredibly dedicated to her work, very talented, and please join me to welcome Professor Krasimira Tsaneva-Atanasova. Thank you, Professor.
Thank you very much, Benoit, for the kind introduction and for the kind words. It's a real pleasure to be here in Montpellier. As Benoit mentioned, we've been working together since several years, and I have been many times to Montpellier. It's a beautiful place. I'm really pleased to be here today and to be enjoying Montpellier again, especially after almost 2 years of pandemic and lockdown. I'd like to start by a disclaimer, kind of. As a mathematician, what really excites me is to apply creatively mathematics to real-world problems and data, and hopefully to help end users, clinicians, movement scientists, and physiologists, and ultimately patients to use the data that's being collected in a better way, to reveal new information, and hopefully my talk today will give you a flavor of what I'm trying to say right now. It is really the mathematician's perspective on this field. I did start looking at movement science and movement signatures in particular because of Benoit. Before coming to Montpellier about 10 years ago, 9 years ago, I think, to give a talk to his group, he invited me and he encouraged me. That was an incredible experience. I did not know anything about this field before that, and it's been a fascinating journey that has opened a lot of different projects. So I will start today. Well, I think I have an outline. So today I will introduce a concept, a notion that we developed during a joint project coordinated by Benoit, a European project related to individual motor signatures and similarity. The focus, as Benoit mentioned, is being on personalization, and my personal interest is also on interpretation, because it's really important to get most of the data is to be able to interpret it. And many of the quite widely used algorithms and methods are somewhat black boxes, and it's hard to interpret why exactly they're performing the way they are. And when it comes to humans, not just to humans, but in this case as well, it can be really beneficial if there is interpretation to some extent. And I'm going to show applications to schizophrenia, which was part of the European project, and then some more recent work with applications in developmental coordination disorder. So starting with the notion of individual motor signatures, I did mention the European project that we worked together, and it was aiming at creating an artificial agent through the concept of similarity in order to enhance social competence in patients suffering from social deficits. And the artificial agents that were envisaged were avatars and robots, and the similarity concept was kind of central to this project. So very quickly after the start of the project, we identified this paradigm as the main task that will be investigated in the project. It's the mirror game, and it is something that is widely used in practice and in various fields. For example, in sports, like martial arts, in improvisation theater, for teaching kids social skills in kindergarten, as well as in some rehabilitation for elderly. In the context of the alter ego project, the mirror game was implemented, as you see here in this picture. It's an actual picture taken in the lab here in Montpellier, and we had like strings. We had a ball that moves along a string, one-dimensional movement, and two people basically instructed to interact via this setup in several different conditions, either by themselves or without paying attention to each other, or following, leading each other, or jointly improvising. And this is an example of the data that came out of this initial pilot implementation of the mirror game. And as you can see, it's relatively like real world data. It's quite, although one-dimensional, it's quite complex and irregular. So the question that we were asking ourselves is how really to quantify, measure, and assess similarity in this quite complicated time series that we were collecting. And in parallel with the experiments that were going on in Montpellier, in Bristol and late Exeter, we were developing a virtual player kind of algorithm that would allow us to implement the mirror game as an interaction between a human and a computer, and later that could be translated to an avatar or a robot. And this is just a schematic representation of the cognitive architecture that we came up with. It involves like a model, which is a mathematical model, also some control elements that allow to couple the computer to a controller. In our case, it was a lead motion controller, and we did perform experiments with the mirror game by interaction between the computer and the human, the student. And you can see here exactly how it looks like. There is a lead motion controller there that detects the movement of the finger, and the computer reacts. It's a bidirectionally coupled interaction with the human player and the algorithm that's implemented in the computer. So this is here an example of the time series that came out from the experiments that we did in this setup with the mirror game with the virtual player. And you can see they're very similar in some sense to the ones collected in the pilot study where humans played the mirror game. And what we also did in this setup is it allowed us to study the time invariance of the properties of these time series. In other words, the same player played or repeated the same interaction on different days, in different weeks. And here, what I'm showing is the same player playing the game 2 different days, and here is another person playing the game. And we can see, maybe this is similar, but the question was really how to quantify this similarity. What is the measure to measure it? And secondly, how to calculate how far or close that these objects are. So, again, that same question. So, after some time, we came up with this notion for auto-signature, which I will try to summarize here in this slide. Basically, we represented the movement by calculating the velocity based on the position time series, and then binning the range and collecting the values of the velocity time series into an object, which is like a frequency histogram or a probability density that we call the velocity profile. So this is what we identified as a model signature that characterizes or represents these movements. And here we can see the velocity profiles of the signatures that corresponds to these two and the other one. So having identified these individual model signatures, we had to ask the question how to compare them. And in the case of these kind of objects, probability densities or histograms, we found a measure, the so-called Earth movers distance measure, that is suitable, and I will tell you in a few slides why we were confident that it's a suitable measure to calculate how far apart or how close these objects are. But first I just want to introduce very briefly and very simplistically what does Earth mover distance means. So if we have to compare the blue and the red histograms here, what the Earth mover's distance do is basically transforms the blue into the red object and takes the difference as a measure for similarity or dissimilarity. In this case, these white bars are the difference between the different blues and the red. And this is here an example of now a quantity. If you take a normal distribution and the uniform distribution that are very different from each other, the Earth mover distance calculated by this formula is here a number 0.714. It's the difference between the cumulative density functions. And in the case of more similar objects, like two normal distributions, we have they're more similar, so smaller distance between them. This is a nice measure because it represents a metric. In other words, it preserves these properties, and as a proper metric, allows us to actually quantify rigorously the distances between these signatures that are distributions in our case. And I just want to note that Euclidean distance would have not been appropriate because this doesn't satisfy when you're dealing with histograms the metric property requirements. So this is now what we did with the data using this framework. These are here now the velocity profiles of one individual and then another one, the corresponding histograms. And here we can see that go back. So the distance between the velocity of the signatures of the same person is 0.04 in this case. And if we look at the distance between two different people, we get order of magnitude higher distance. In other words, they're more different. And yeah, in this way we can compute all these distances between all participants in our experiment. So having a proper metric as the Earth mover distance, we can then apply a dimensionality reduction technique, the multidimensional scaling in our case, that allows us to map each player's function over space. Here x and y represents the two. So if you're familiar with principal component analysis, which is another type of dimensionality reduction technique, you can think of x and y as the two principal components, although they are derived from following different considerations in the case of PCA. So here these are the most significant dimensions in this space. The space is huge because we have many trials, many humans, a lot of data points. So now projecting this onto this plane, what we can see here, each color represents individual, and each symbol is the same individual performing the mirror game on different weeks. So we can see now one individual very consistently, and this is quantified by the distances between the individual signatures, is positioned in that part of the plane. We can see another individual here, much more variable, but clearly different. And then we can map all of our participants in the space, and then we can quantify how different or similar in their movements in the mirror game these people are. And what's also nice, we call this space similarity space, for the reasons that I just explained. What's also nice is that we were able to interpret these dimensions. For those of you who have used dimensionality reductions, you know that it's very difficult, usually impossible, to say what the principal or the most significant dimensions correspond to. But in our case, it turns out that the most significant one here, x, corresponds, it's almost perfectly correlated with the mean velocity of the movement, which is not surprising given that our velocity profiles are based on velocity and the range. And then the second most significant dimension, which is the y, is correlated quite well with the mean kurtosis. This is a higher order moment that describes distributions, and in this specific case, it corresponds to the shape of the distribution. In other words, the higher y is, the more peak the distribution is, the less variable the movements are. And here, if you go along the x direction, the movements of the individual become faster and faster. So, using these concepts and this framework, then we went on into analyzing the data that was collected in the Alter Ego project in interaction, playing where the mirror game was performed between an individual and an avatar, as well as a robot, and we had healthy and patients with schizophrenia. And something that came as a bonus pretty much from this project, something that wasn't envisaged originally, was the fact that we were able to identify, we call them biomarkers, but these are really properties or characteristics of the movements that allow us to classify or to distinguish between healthy individuals and patients with schizophrenia. So the participants that were involved in this project, here is just a list of how many controls and patients we had and what kind of trials they did in the case with of interaction with the avatar or the robot. The features that we use for classification are summarized here in this slide. It's very busy. All the details are actually explained in the publication that came out. What I like to point out is that overall we used 5 features, and each of them, what's important for each of them, they were described in terms of frequency histograms or probability distributions. And they were related to the properties of the solo movements in terms of the frequency content and duration of movements between each other. Also, we had movements from one point to another. Also, we had a model that I don't have time to show now, but we used the distributions of the coefficients of this stochastic model as features, and as well as we had 2 features that were related to the coordination between the virtual player and the human, and they're related to the relative phase and the coherence of this coordination. So the results of our classification are summarized in here. So we had, due to the small number of participants, relatively small, for machine learning classification, we used something called leave one out, where we train on all participants except one, and then we test the performance on one of them, and then we repeat this for all of them. But and then we take majority vote at the end to come up with the final measures for specificity, accuracy, sensitivity, and precision. And we can see here that the developed algorithm is almost perfectly identifying healthy controls and very well, relatively very well. It's also doing with patients with schizophrenia, and yeah, we were very pleased to get measures of specificity and precision equal to 1. We validated this algorithm on the experiments done with the ACAPS robot, and we also compared it to traditionally clinically collected data on neurological soft science. We also verified that these results don't depend on the dose of medication that the patients with schizophrenia are receiving, and yeah, we published this paper. Since then, we have been taking these ideas forward, looking at developing diagnostic tools for clinicians that are facing, this is collaboration with the NHS trusts across the Southwest, patients with psychosis, and specifically first episode of psychosis, so unmedicated patients, usually young people. This is a big challenge. I learned through my interactions with these different specialists that almost 70% of young people that present with symptoms or with some problems that can be attributed to psychosis are misdiagnosed. They're either given medications where they shouldn't have, or they're not given medications where they should have. So it's a big problem that faces the services in the UK. So what we did here is a little feasibility study, it's still ongoing, is implementing the mirror game on the computer, basically translating the outer setup onto a portable collection system that can be easily used in clinical settings, and going out to the various places where patients contact the services, collecting data. And so far in that feasibility study we have had 86 healthy and 32 service users, as they're called. And we have also got some feedback in terms of how they perceive this as a potential game that they can use to aid diagnosis and to help being diagnosed better. And we have got some very positive feedback as summarized in this table. They would be happy to take this home. They enjoyed doing it, and some not so positive feedback. So there is a lot more work to be done in that space. So we also more recently, now moving to the next part of my talk, have been looking at data from children with developmental coordination disorder, also known as dyspraxia. This is associated with difficulties in coordination, as the name suggests. And in this project, again, relatively small project, we were working with collaborators from Sports and Health Sciences in Exeter, funded by a charity that is interested in this condition. Basically using the game, the mirror game, as I have already told you about, but in addition to that, data was collected in a setup that you can see here. Basically children were equipped with eye tracking glasses, and they were also lifting objects with different sizes and different weight, and the force or the grip was measured during these experiments, as well as the eye movements. So and this is, so I have to say this is preliminary data, and this is really a project that finished a couple of weeks ago. These are the initial results, applying that framework of individual, that notion of individual mode signatures that I already described to you. So basically using these probability distributions. Here we look at the relative phase in the mirror game, and these are two examples of a healthy and a child with dyspraxia. And then here is the representation in the so-called similarity space, and we can see clearly a subgroup of patients that is very different from the healthy controls and some of the others. We also did this with the force of the grip that they exert when lifting the object. Here are the probability distributions that we obtain, and again, here we can see a subgroup of individuals that are very, very different. And finally, the eye movement's velocity here is an example of how this data looks like, and here we can see the similarity space in this group of children that are very different again. So basically, in all these three methods that we examined, we identified subpopulation in the group of children with dyspraxia, and we call this visual motor signatures. We believe that these identified signatures in the specific task can help develop personalized interventions. We still need to do work in terms of mapping these subgroups to some clinical measures or some other conditions that these children may have. Those of you who are familiar with dyspraxia probably would know that many children that have dyspraxia diagnosis, they also may have ADHD or they may have autism. All I know at the moment is that these are different subgroups. They are not the same. They don't overlap. And we're going to be looking and interpreting them better and linking them to something that could be useful in terms of personalized interventions. So talking about intervention, this leads me to the final part of my talk. So here we are again looking at developmental coordination disorder, but this is a completely different trial, different group of children, and different question. In this situation, basically children with dyspraxia were trained to perform an intervention that is associated with throwing a ball against a wall and then catching it with a target on the wall. I don't have a picture, but I guess you can all picture this thing out. You just throw a ball and then you catch it. And there were two groups. One of them was instructed to do the task by some traditional means, and the other group was instructed to do the task by first fixating on the target on the wall, and then for a few moments, and then following the movement of the ball when performing the throw and the catch. And in this paper here, this is described in detail. The study was interested in whether the training where they called quantifying, where children are using fixating on the target of the ball, are performing better after a certain time of training, or compared to the technical training, the traditional training group. And they did find that children improved their gaze control and catching coordination following the quantifying training compared to the technical training. When we came into this work, that paper was already published, and we were approached by the group of scientists, part of them at Exeter as well, with this additional data that they collected during the trial associated with the upper body movements during the throw and catch game. So basically, they had more than 6 sensors, but we ended up using 6 of the upper body sensors to kind of try to interrogate a bit more the data that was collected and look at coordination and how this may be associated to the results from the intervention. I should mention that they measure improvement in coordination in this game by something called catching score, and that is a clinically well-defined measure, and it is scored by a clinician or practitioner that is familiar, that is a specialist in developmental coordination disorder. So the question that we asked was, can gaze training encourage the emergence of self-coordination via self-organization in children with dyspraxia? And to do that, again, we looked at identifying some sort of signatures. We started with probability distributions, but they turned out not to be suitable, and again, this is not surprising. We're looking at coordination now here, and we have six sensors on the upper body of the children. So what we came up with in this case is to compute or to use covariances that are measures of coordination between the time traces detected by the sensors, and construct something, an object, covariance matrix, which gives the covariances between each and every one of these sensors. And here is the formula how you compute covariance. And having identified, so we can compute these covariance matrices for each of the participants or each of the children, then we had to compare them. Again, the question about distance. So in this case, we had to use something called Riemannian distance. I will show you what it looks like on the next slide. It's given by this formula, and it is a metric that is suitable for comparing covariance matrices. So having a metric and a signature, we can then perform again multidimensional scaling and compare these different individuals in that similarity space. So yeah, in this case now, just to put it into context, the individual node signature or movement signatures are given by covariance matrices. And everything that I'm going to show you in the next few slides relates to these matrices and signatures, as we call them. So what is the Riemannian distance? I borrowed this from a recent paper in Neuroimage. It's actually something that comes quite often when functional networks are being derived from data. In this case, the matrices, including the covariance, are symmetric positive definite, and they live on a space that is not Euclidean. Commonly, these spaces are called Riemannian manifolds. In this case, it is a cone. And as this example nicely shows, that's why I borrowed it. So the distance between objects that are represented or that live on these spaces are given by geodesics. And if you compare them to Euclidean distances, you may get completely opposite results. So for example, in this case, the geodesic distance between A and B is shorter than that of A and C. So A and B, this red thing is shorter than A to C. However, the Euclidean distance between A and B is bigger than the one from A and C. So this is just a point to make here how important it is to use the right measures and the right quantities when comparing and dealing with data. So a few more slides just to show you the results from this analysis. First, we looked at the relationship between improvement in the catching score and total coordination that was given by properties of these individual mode signatures or covariances. And what you can see here with green, the group of children that were trained using the quad-eye training, and the group of children that used in red, that used the technical or traditional training. And what we can show here is that there is a good correlation in increase in total coordination and improvement in catching score for the quad-eye training group, and it's pretty much not there for the other group. We also, that framework also allows us to kind of visualize and review the huge intra and interpersonal variability in coordination patterns of individual participants. Again, here we see in green we see the quad-eye training group and each child. In red we see the one that were trained using technical training. In gray you can see the average performance of individuals, and baseline is the performance in this task before training. And you can see that everybody found a different way of or responded in a different way following this training or this intervention. Finally, we decided to look at those that really improved. In other words, they have catching score of more than 8. And here again, the same convention. We have red for the technical training, green for the quad-eye training, and blue is the baseline. It's before they've been subject to intervention. You can here also see the various kinematic measures that were, or the various kinematic measures that were detected by the sensors on the upper body. So we basically found that this picture here supports our hypothesis that quad-eye training allows for self-organization and emergence of individual coordination patterns that are different from those at baseline. This is seen by comparing the green and the blue, and this is not exactly the case for the technical training. The red and the blue circles there pretty much overlap. But what was really interesting to me that came out is like shown in these, by these covariance matrices. These are individual children that have improved significantly in their score, and we can see that each of them found a different solution to improving their performance in terms of coordination of their upper body kinematics. So this really leads me to the end of my talk. There is a lot more to do, and I personally believe that we can use this information. Well, I know we can. We just need time, money, and people to develop further understanding of how these individual solutions emerge in this specific task. And I know this is also applicable to other situations as well. So, finishing with some acknowledgements, really, Piotr has been with us from the Outer Ego project and continues to work at Exeter and has been in the heart of all that I showed you. Has been instrumental for obtaining this insight and this knowledge. And here I also would like to acknowledge the colleagues, students, and academics at Exeter in Sports and Health Sciences, as well as the Outer Ego team, that without these people I would have not been able to show you what I told you today. Thank you very much.
Wonderful, Krasi. Thank you so much for this wonderful talk. We have a bit of time for questions. So I don't really see anyone, but if you have a question or a comment, it can be in French or English, please raise your hand. You can have a mic. At some point, there's one here. There's one. Did I see a hand up there? André is one. Then I've seen Stefan here.
Hello. Here. Thank you, Krasimira. I'm here in the center. Thank you for your presentation. I was wondering about the universality and the transferability of the motor signatures. So if you change the task or you inject more people to the group, so the landscape of the multidimensional scaling would be changing. And I was wondering about your vision for the future, what tools can be used or should be used for getting the IMS that would be extractable, no matter the task, no matter the group.
I'm not sure if I heard very well, but you were asking of how universal. So in terms of measure as quantities, they're as universal as you can get. Basically, as long as you have the right object creating some sort of distributions, and you compare them using a distance that's a proper metric, then it's absolutely fine to project them into a space using multidimensional or dimensionality reduced. So although I only showed 2 dimensions, a plane, actually it has many more, and it's up to the user to decide how many dimensions they might want to use. For the classification, we actually used 6 of these dimensions. You can't visualize this. 6-dimensional space is not possible to visualize, but there is definitely information in more than just the 2 dimensions in some cases. I'm not sure if I'm answering the question exactly, but all I can say is these are mathematical quantities, so they're like the truth. So it gets complex. The task-dependent part is up to the scientists that have designed the task, and then analyze the data to interpret what exactly it means. And I tried to make this point a few times. If you noticed, almost all the examples that I showed, they weren't designed to do this analysis, so we did not know what the analysis will be when the data was collected. So if you if you start designing the task with a priori having in mind how you might analyze it, then you may be able to get better results. Again, I'm not sure if I answered exactly what you were asking. We can discuss later.
Yeah, we have plenty of time, you know, during lunch, break, etc. I would like to take as many questions as we can. We have 5 minutes. Stefan.
Thank you for your presentation. I would like to see how do you interpret or correlate your MDS axis with original data, and if you can go back to your motor signatures of alter ego project.
So which one, Stefan? The one with the correlation?
Yes, the one.
Yes,
this one. So if we go back to your first axis, they are invariant to rotation. No, please go back to the two-dimensional projection of
here.
Yes, the x and y. This can be another x and another y if you rotate this set of points, and the distances will be the same. So how can you correlate x and y when this is a rotation invariant with original data? This is my issue.
Yes, so that correlation is completely independent. Basically, you see here, this is just a subgroup of what you see here in the next slide. So this is here all the data, many more people. So basically you take that x and then you compute the mean velocity of all these participants, and then you just look at whether they correlate. It's not anymore related, so this axis is taken from here, and this one is now the mean velocity of the movements that created these objects. So that they don't depend on each other, in a sense. The only dependence is that the data that is shown here is the same that the velocity comes from. And that is the x-axis that you see here. So it correlates perfectly with the mean velocity.
Okay.
Okay, thank you.
So
We have time for... Yes, please.
So you, the first part of the talk, we were talking about motor signatures. I'm here. You focused on temporal aspects. So does this correspond with what you said visually, or whether, or did you focus on temporal aspects because it was technically more doable?
I didn't catch everything, but so the temporal aspects and what?
Yeah. So in the first part, when you talked about motor signatures, you had velocity and you had frequency. So you were focusing on temporal aspects, right? Yes. So was this does this correspond really to what you saw visually, or did you see other things and you focused on the temporal aspects because it's technically doable?
Well, we saw a lot of things. I mean, we tried a lot of different things. The velocities are, and in the literature, so you see here examples of the data. So we did calculate all sorts of things here. You can calculate frequencies, you can do Hilbert transform, and we did. You can look at various things. But what we found out in that preliminary exploration was that the velocities are the best representation in terms of carry the most information about these signals and in this specific task. And they don't have to be velocities necessarily, as showed you later in the biomarkers for schizophrenia. We use different characteristics of the time series.
Is that okay, Zoe? Okay. And we have time for a final short question. So we have 43 seconds. So Krasi, the dynamics of those IMS over time, so across ages, across ontogenesis, it was all kinds of changes that we all go along with. Can you tell us a bit something about that, like the permanence and stability across time?
That actually is a very interesting question. In any of these things, we haven't really compared or followed an individual through, well, except the last part where I showed you the covariance matrices that we follow people before training and after training. And you can see that change, that evolution of the individual mode signatures. And I believe this is actually really fascinating in terms of understanding what, or revealing what mechanisms might be in play and are responsible for this evolution. I guess the last bit was the most pertinent to your question.
Thank you, thank you. Thank you, President. We do have, thanks to the organizers, we do have a gift for our speaker. Thank you very much.